Before we get started, yeah, I just wanted to thank the organizers, the event staff for putting on this awesome event. I've had a ton of fun just meeting people and listening to presentations. And yeah, hopefully this one's interesting to people as well. Cool, so let's jump in. Yeah, for today's presentation, I'll be telling you about ReadOptimized stores, which is a pretty critical piece of infrastructure at Airbnb that powers many of our data serving systems. Again, a little bit about me. Thank you for the introduction already, but yeah, I'm a software engineer at Airbnb, working on the data frameworks team. We build tools and platforms to help improve the productivity of other teams, specifically around data processing at Airbnb. Yeah, so before I get started, I want to ask a question. How many people have used Airbnb before? Cool. Yeah, that's a lot. That's awesome. So I'm not sure how many of you knew this, but Airbnb was actually founded in San Francisco about 15 years ago in 2008. The story was that there was a design conference in town, but not enough places to stay. And our founders, Joe, Nate, and Brian, hosted the original Airbnb guests on air mattresses in their living room in their San Francisco apartment. And then in the morning, they made them breakfast. And as a result, Airbed and Breakfast was born. So since then, Airbnb's come a really long way. In 2016, we launched Experiences to try to expand on Airbnb's vision to provide the magical end-to-end trip, not only providing unique places to stay, but also providing guests unique things to do, designed and led by local hosts. Skipping ahead a bunch of years, at the end of last year, we hit some pretty big milestones. So at the end of 2022, we hit 1.4 billion Airbnb guest arrivals for all time. Guests have the choice to choose between 6.6 million listings across 220 countries and regions around the world. And these were hosted by over 4 million members of our incredible host community. So yeah, it's been pretty awesome to see Airbnb scale over the years and just grow. But Airbnb has also run into a huge number of scaling challenges during this time. For today's talk, I want to focus on one specific piece of infrastructure, which is ReadOptimized stores, that helped us get through some of these scaling challenges over the years. And in order to talk about this piece of infrastructure, I'm going to zoom in on one specific part of Airbnb's product, which is the Airbnb listing page. Cool. So for anyone who's used Airbnb before, this page might look familiar. And for anyone who hasn't, this is one of the most important pages in Airbnb's product because it's where guests go to sort of like browse all of the listing-related information before they book. So for example, on this page, guests can browse things like listing photos, they can read reviews, they can read listing information, they can also look at like pricing and availability. So let's dive into sort of what the architecture would look like behind this page. Oh man, it looks like my formatting got a little messed up, but that's okay. So if we look on the left, there's a picture of the Airbnb listing page. And on the right is an example of what the architecture can look like. So starting off in the early days of Airbnb, what the architecture might have looked like is you might have a web server that receives requests from clients. And then the web server would call into a single database containing everything. It would then get the response and then generate a response for the client. So overall, a pretty straightforward and pretty simple architecture. Over the years, as Airbnb's product grew more complex, the architecture evolved as well. So instead of calling a single database, the web server might first call a listing database, where it might look up listing-related information. Afterwards, it might call into a user-related database to look up things like superhost status or user profile photo. Next, it might call into a reviews database to look up reviews information. And lastly, a pricing database to look up what price and availability we should show users. In general, we call this model an in-memory join because a single web server essentially calls all these different databases, gets the data back, joins it in memory, and then returns it to the client. And this is the model that most services at Airbnb follow. And for the most part, it works pretty well. It's simple. The web server just looks up the data that it needs, and it returns it. I think where you can run into some challenges is if you have certain high traffic or high complexity pages or services, then this model can run into certain issues. And I'd like to talk about those next. Cool. So looking at a couple challenges that you can run into. The first one is around reliability. And oops, sorry, I went ahead. Yeah, so what are some challenges you can run into with reliability? Well, essentially, when you're calling all these underlying data sources, if any of those calls fail, your web server might not be able to generate a response, and that call might fail as well. Latency can be an issue as well, where basically the web server has to wait for its slowest dependency to return before it can also return a response. Historically at Airbnb, this has actually been a problem with availability, where you can have many complex overlapping sets of rules around booking windows, minimum booking lead times, just many different sort of restrictions around whether or not we should show a listing as available. That can be pretty complicated to calculate. In general, these can also be difficult to cache, as guests can search by many different dates, different guest counts, and those can all impact availability. One last challenge you can run into with this in-memory join model is you might have teams like the reviews team or the messaging team that want to support features like free text search or searching across databases and tables. And in general, certain native database implementations like MySQL might not support this kind of feature very well. One thing to mention also is that this is a very simplified architecture. In reality, Airbnb's architecture looks more like this. And you can imagine sort of as the number of dependencies grows, these problems just kind of get even more out of hand. Cool. So what's the solution to all these problems? Well, one solution that teams adopted at Airbnb over the years is this pattern called materialized views. And I'll talk about how those work next. So again, here's our in-memory join model, where we have a single web server that calls into multiple databases, gets the data back, joins it together, and returns it to the client. Under a materialized view architecture, instead what we would have is you would set up an indexer service that consumes mutations from databases and basically looks up any other data it needs whenever a write happens. It would then pre-calculate a document that contains all the data that the page needs to load and store that in some sort of storage that we call a materialized view. Some examples for this that might sound familiar are Elasticsearch is a pretty commonly used one, or Redis, key value store, but you can kind of plug and play anything that you want. So the whole idea with this architecture is that later on, when the client makes a call, to the web server can directly call the materialized view. And one way you can think of this is that in the first model, in the in-memory join, sort of all the calculation and computation happens at read time, right when it receives the request. In a materialized view architecture, anytime a write happens, this indexer service basically pre-calculates all the data needed and stores it in the view so that when you actually serve the request, it can be very fast. Yeah. So over the years at Airbnb, we saw many teams sort of adopt this pattern, just all around the company organically. They had very expensive pages to load, and naturally this was a choice that they, a pattern that they chose to adopt. However, they also started running into problems, and I'll talk about this next. Cool. So one challenge that teams ran into while building these materialized views is that they each had to, oh man, this got messed up too. Sorry about that. One thing that they all ran into is that they all had to implement their own custom consumer logic. So basically, they each had to write sort of listeners for each database. They had to write their transformation logic within their indexer service, and they had to write their own sort of custom adapters to write into materialized views. Teams also in general had to create mechanisms to handle versioning and concurrency. Basically, race conditions can occur across separate databases from simultaneous writes. And you need to handle that so that you don't overwrite your view with older data. And some teams just completely chose to ignore this. One last thing that teams ran into was sort of a way to basically, we have the indexer service that's online and it streams updates, but we still need a way to populate the index with the initial data, kind of like when you first spin it up or if you make schema changes. So basically, teams implemented online and offline jobs in order to bootstrap their indexes, but they all ran into various problems as well. In general, there was a pattern. Many teams at Airbnbs wanted to utilize materialized views, but they ran into difficulties basically in building and maintaining these services. And overall, it was just very painful for them to sort of maintain this. It was also around this time that people on my team noticed these patterns, and this is exactly where the ReadOptimized stores framework comes in. Cool. So the goal of the ReadOptimized stores framework, or as we call it, the ROS framework, is exactly to solve the problems described earlier. Basically, we try to provide simple building blocks to enable people to build these materialized views in order to solve their product use cases. So next, I want to talk about how the ROS framework works at Airbnb And to do that, I think the easiest way will be to showcase kind of like if we were clients, how we would build a pipeline. So I'll jump into that. Cool. So this is the listing page from earlier, and we're going to use this example again. The first thing clients would provide is a GraphQL query that should contain all the data that they need in order to render the page that they're trying to build. So for example, if we're trying to build a materialized view for the listing page, we might want to include information like the listing title, or pricing information, or reviews information. We chose GraphQL specifically because this is a language that many of our client teams were familiar with. Many of them are more product-facing teams, and in general, Airbnb, most of our APIs are implemented in GraphQL. So this was a language that we thought would be most familiar to people and help them onboard quickly. Cool. So after writing the GraphQL query, clients can also optionally provide business logic that can be used to sort of calculate aggregate or derived fields. And one thing to note is that we take this GraphQL query and generate a Java object with the exact same shape that clients can then manipulate. One example of something that you can do in the business logic is, for example, with the listing page, maybe you want to take the reviews and calculate an aggregate review score in order to show guests that are browsing the page. And this is the sort of thing that can happen in the business logic. Cool. So that's pretty much the client interface to ROS. Let's take a look at what happens under the hood. So the first thing that happens is the ROS framework takes the GraphQL query and business logic provided and generates an online stream job that basically consumes updates from the databases and writes it to the sink. So we refer to this as a ROS pipeline or ReadOptimized stores pipeline because it takes input data from one side and outputs it to the other. In terms of the input data, again, it's database mutations from the databases earlier. And what the ROS framework does is it takes the GraphQL query and it generates consumers that knows exactly what databases to listen to and sort of what mutations apply. From there, we call back into database replicas in order to fetch any additional data needed. Then we take the client business logic and basically apply it in a transform step we take the data returned in the earlier step, we apply the client transformations in the business logic, and lastly, we write it to the sink. And so summarizing, putting this another way, essentially clients provide us a GraphQL query in business logic, and we generate them a real-time streaming job that consumes from databases and keeps the sink up to date with those mutations. There's also one missing piece, which is on the offline side, like how do we bootstrap the index? And the ROS framework handles that as well. So instead of consuming from databases, we consume from database snapshots in our data warehouse using Apache Spark. So using the exact same interface of GraphQL query and business logic, we first generate a batch query using the GraphQL shape, and then we run the exact same pipeline logic and basically backfill the results in bulk into the sink. So summarizing again, basically clients provide us this query and business logic, and we not only generate them an online job, but they get an offline job for free as well. So that's the majority of the architecture for the ROS framework. Other things that clients get when they use the ROS framework are, for example, a standardized set of dashboards and alerts. Here, for example, is one sort of shared dashboard that clients have access to. And you can see on the bottom left, we have some metrics around how many database mutations are we processing. And on the bottom right, you can see a metric for end-to-end lag, which is whenever a database mutation occurs, how long does it take for the data to be propagated into the sink? One interesting thing is that this particular dashboard is actually used for capacity estimation. So you can see kind of midway through the mutation events diagram that there's a big sort of jump in these yellow events. And what happens in the capacity diagram is the blue line is current usage and the purple line is max capacity. And you can see that we actually start exceeding the max capacity of what the pipeline can handle. As a result, on the bottom right, then we see propagation lag start to jump. Yeah, so in general, we use Datadog pretty heavily for these sorts of like metrics and monitoring and dashboards. One other thing that we provide to clients is alerts. So we make pretty good use of Datadog monitors, and most clients have these enabled as well. Cool. So that's an overview of ROS architecture. Next, I want to dive into one specific challenge around concurrency that we ran into, and maybe this will be interesting to people. So to talk about this, I'm going to start with one example race condition that we ran into, and then I'll talk about how we solved it within the ROS framework. So in this example race condition, let's say that we have two databases. We have a listing database, and we have an availability database. and the availability database contains an initial value of false, meaning that the listing that it corresponds to is unavailable. And let's say that we have 2 threads, and we're going to look at a timeline of events for what happens. So let's say that at time 1, there's a listing mutation. And what happens is the listing mutation is produced by the database, and it's consumed by thread 1. And at that time, thread 1 will call into the availability database and read the value false, and it'll store this in memory. So listing ID 1 has is available set to false. Jumping ahead to time 2, let's say that the first thing that happens is thread 1, for whatever reason, goes to sleep. So it's just sitting idle. And at this time, let's say that there's a simultaneous update in the availability database setting availability to true. So like, let's say the host just basically set their listing to available. At this time, the second thread would receive the availability mutation and call back into the listing database and basically store in memory listing ID 1 with is available as true. So jumping ahead to time 3, let's say that the first thread is still sleeping, and then the second thread writes this data into the sink. So one thing to note is that the sink is now correct. It has is available as true, and this correctly reflects what's in the initial database. However, I think some people can probably see what's about to happen next. So let's say that at time 4, again, thread 1 wakes up, and at this point, it still has is available set to false, and it writes this to the sink. Well, now we have a problem, because the data in the sink is incorrect, and if anyone reads this, they're going to get incorrect data. So how do you solve for this? I'll talk about how we did it within ROS. This is the architecture from earlier that showcases a ROS pipeline, but it's actually not totally correct. In reality, ROS actually supports 2 types of pipelines, which are source pipelines and notification pipelines. Zooming in on source pipelines, the sole purpose of source pipelines is to read from databases and generate what we call notification events, which are basically Kafka events that it writes to a Kafka topic. The notification event contains one single field, which is called a document ID. And this is the ID of the eventual sync document that'll be updated. So the notification pipeline reads these notification events. And the first thing that it does is it takes the document ID and looks up any additional data it needs from data replicas. And then from that point, it applies transformations, and it writes this document to the sink. And again, you can see the document ID here, which is a unique identifier for the document in the sink. So one way to think of this notification event is it's basically a way to tell the framework that some update has happened, and that the framework needs to go and refetch all the data associated with this document ID and just update it in the sink. One other thing about this diagram is, in reality, most ROS pipelines consume from more than just one source. So you might get something like this, where each of these source pipelines is auto-generated based on that GraphQL query from earlier, but reads from an individual data source, publishes these notification events, and then writes that data to the sink. One really nice part about this architecture is it really simplifies each of the components of the pipeline. So the source pipeline's only purpose is to take whatever database they're listening to and map those mutations into document IDs. And then the notification pipeline, regardless of where the mutations are occurring, all it needs to know how to do is take a document ID, rebuild the full document, and write that to the sink. Tying this back to earlier, the concurrency problem, the way that we solve that is that it's actually pretty solely based on the usage of Apache Kafka. Basically, within Kafka, we can partition the topic by document ID, which will essentially guarantee that all updates for one single document ID are only processed by a single thread. And then we can basically avoid all the sort of concurrency problems that were described earlier. One last thing I'll mention is that whenever the notification pipeline starts processing the events, we also stamp the event with the current timestamp, and we store that as a version within the sink. This is really useful when you have multiple things writing to the sink. Like, for example, when the offline backfill job's writing to the sink, you can basically do a version comparison and guarantee that it's never overwritten by older data. And there's no more content on this slide. That's all the content. So yeah, that's pretty much an architecture overview of how we solve for concurrency and versioning within ROS. Cool. So yeah, I guess for this next part, I'll just quickly cover some current adoption within Airbnb. We currently have about 25 teams using the framework with over 80 materialized views or indexes in production. Across all our ROS applications, we handle over 20,000 events per second. And in general, teams adopting both ROS and materialized views see very significant improvements in reliability and in latency. For the last part of the presentation, I want to talk about some learnings that we had. The first learning is that basically, investing in interfaces has had a huge impact on developer productivity for us. Specifically, our interfaces of the GraphQL query and clients providing business logic is basically, it's something that's very familiar to clients, and it's allowed them to onboard pretty quickly while allowing us to make significant changes under the hood without impacting them at all. In general, working on a platform team, we feel like it's been really valuable to invest heavily in the right interfaces early on, since this not only has helped us improve customers' experiences with our products, but also helps us keep our code more maintainable in the long term. So we've been happy with our code interface, but one area that we have been trying to work on more is around our ownership model, and I'll dive into that next. So the learning here is platforms enable scaling, and I'll talk about what that means. So this is, again, kind of a simplified picture of our architecture from earlier, where on the top we have a client indexer service that consumes from databases and writes to the sink. And then on the bottom we have your offline bootstrap job, which consumes from the data warehouse and writes to the sink. So one thing to mention is that right now clients provide us this client logic, and we generate all these components for them. But afterwards, in reality, all of this becomes owned by clients. So they're responsible for things like monitoring metrics, responding to alerts, and basically all the other aspects of ownership. So when we first created ROS, we made this assumption and intentionally kind of set up this ownership model where we would generate them components and then they would own their services. And this was because we made the assumption that client teams had more sort of product context or like domain expertise, and that they would be better suited to define their joins, configure their services depending on the traffic patterns that they have. Like we assume that because they have this product context, they would essentially be better suited as owners. But in reality, I think we've been realizing that this ownership model is a mistake over the last couple of years, or maybe not so much a mistake, but that it's difficult to scale this ownership model in the long term. Like clients have this sort of context on their products, but in general, to operate like a stream processing service, there's a lot of additional context that you need that our clients don't necessarily have or like want to learn. Some examples include figuring out how to properly tune Kafka according to the traffic that you have, or on the offline side, like tuning Spark. Or kind of another one is making sure that your offline bootstrap job doesn't compete with your online job for resources, because then like a backfill job could sort of block out your online job from processing updates. So anyways, we've been running into challenges with this, and we have a plan to try to improve this in the future. And the plan is that instead of clients owning a single indexer service, we're planning on building sort of like a ROS platform on the online side and a shared offline job where sort of similar pipelines where clients still provide us, they essentially provide us their logic and we generate the pipelines. But the main difference is that we overall own the architecture. We sort of guarantee them that their data will be available, but we own all the operational aspects. And we think that this will help basically more people onboard, and it'll help scale ROS in the long term. Tying this back to the learning, platforms enable scaling. I think this is sort of one pattern that we've seen in general at Airbnb over the years. Like I remember when I first joined, teams would, for example, if you're on a team, you might need a database. And so different teams around the company would all have to provision their own database, pick exactly how many resources they needed. If they got more traffic, then they had to basically manually scale up their database. They had to understand like the cost implications. And you get to some point and there's 50 different teams doing this, and it doesn't make sense anymore. It makes more sense to create a centralized storage team that can sort of handle all these complexities and just expose an API, and then have all the other teams around the company just use their API and not have to worry about how many additional whatever resources I need to scale my database. So this is a pattern that we've seen at Airbnb, and I think is pretty common around other companies as well. And that's a pattern that we're planning to adopt with ROS. One last learning that we have is that under the right circumstances, materialized views can be a pretty powerful tool. For example, this quote is from Ali from the Airbnb payments team, and it's from a blog post posted in June 2022. Basically, around that time, they migrated several payment services onto both the ROS framework and just starting to use materialized views in general. And you can see they saw some pretty crazy improvements in both latency and reliability. Yeah, so I think over the years, Airbnb's product has really grown and gotten more complex, and materialized views have been a pretty useful tool to let us sort of continue to build on that complexity and add more features while still keeping the customer performance pretty good. So yeah, in general, they've been pretty useful at Airbnb, and we hope that they can be useful for you all too. And that's the presentation. So Yeah. If
Thank
I can
you.
say one more thing, if that's
Yes,
okay.
go ahead.
First, yeah, thank you all for listening. Thank you for coming. If anyone's interested in learning more, you can check out our engineering blog. We actually recently published a post on the ROS framework, and we'll probably publish more. One thing is we use our internal name for the project, which is Riverbed, so in case anyone finds that confusing. If you're interested in careers, please check out our career page. And if anyone wants to chat in general, please shoot me an email or message me on LinkedIn, and I'll try to get back to you as soon as I can. So, sorry, thank you.
That's perfect. You have to always put that career page. Good. So thanks, Victor, for the presentation. That was super, super interesting. We have one question in Slido, and then we are going to switch to the room. The question is, certain type of data storage have native implementations of materialized views. So what was the main reason why Airbnb opted to build its own solution?
Yeah, that's a great question. Yeah, so certain databases, like I think SQL Server has, like in other databases, have a built-in materialized view feature. One thing that Airbnb needed to address is, different teams across the company use different types of databases. Like MySQL is common. We had key value stores we needed to support. We have like an in-house thrift store. Teams wanted to consume data from like Hive or offline. And the sort of existing products didn't support these use cases well. So this kind of happened organically. Like teams realized this early on and built their own solutions to consume from all these data sources. And the ROS framework was just an evolution of that. Yeah.
Great. Any questions in the room? Yes. Okay, we got another questions on the Slido. How do you handle multiple mutations to the same record being funneled into multiple views? Parallel event consumers or something else?
Yeah, in general, each of our pipelines is run in sort of like an isolated setting from each other. That's a great question, whoever asked. Yeah, it's kind of like one nice part about our current architecture is that sort of by default, each pipeline is isolated from each other. So it's hard to explain, but like in general, our database mutations also arrive using sort of like an in-house CDC bus based on Kafka as well. And so Kafka handles sort of like making sure that each consumer group correctly receives the message. And then from there, it's like separate. It's a separate pipeline on like a separate service, so it's not too much of an issue.
Good. Any other questions? Yes.
Thank you. Your GraphQL mutations, are you getting those from Apollo Server? How are you actually getting those registered?
That's a good question. So for Airbnb, let me think about how to say this. We use GraphQL kind of at the presentation layer, but we don't actually use GraphQL at the database layer. We have like a sort of a separate schema language across the company. So in that sense, the mutations that we have, they're not actually based on GraphQL. I mean, I'm not sure how much detail to go into, but like basically we consume bin logs and produce sort of like thrift mutations based on that. It's not actually, yeah, they're kind of separate. Like within ROS, we use GraphQL purely for the code generation aspect, and it also ties into our API layer that we can use to do some nice things. Like we can share tooling with them as well. But yep, great question.
Where did you handle the obfuscation of any PII or auth-related data? Because now you have two copies. One there is source of truth in the materialized view. And also, what's the retention of your materialized view? Are you frequently purging it, or it's a long-term history?
Yeah, I'll speak to the second one first, which is the retention. It kind of depends on the data store, but in general, most of our materialized views don't have an expiration. That's not true, actually. I'll give you an example. So many of our clients use Elasticsearch. That one doesn't, like, we don't expire records from Elasticsearch in general. They kind of just stay until they're either overwritten or deleted. You can also, we have like a key value store, and teams do configure like sort of an expiration for records based on what they want there. So it kind of depends on which materialized view you want. And one nice part about the framework is as long as you sort of meet the interface or protocol that we set, then you can adopt it. Going back to the first question around PII, I think it's sort of handled, I want to say upstream of us. Not sure how much specific detail to go into, but yeah, like luckily it's something that at our schema layer we have this tagging that allows us to say, you know, these fields shouldn't be propagated or these ones should. And yeah, it's luckily a lot of it is already abstracted, kind of. So.
Okay, thanks, Victor.
Yeah, thank you all for attending.